All right, so today we're going to be talking about exponentials, and specifically we're going to be talking about it in regards to how it applies to COVID-19. So, as we learned previously in class, we know that natural events, things like population, infections, bacterial growth, reproduction, a lot of things follow an exponential curve if they're allowed to progress naturally. So that means that we're not influencing it, we're not taking any action, we're just letting it run its course. So, I want to analyze some of the data from Houston, Texas, and the United States. And I want you guys to follow along. So, question number 1. They're asking me to go to this graph. So I'm going to go ahead and click this link here. And it's going to take me to my Houston region graph. So I'm going to look at this graph, and this has a plot of days on the x-axis and number of cases on the y-axis. I was asked to turn off the purple one. So if you look, this is all the actual data that was gathered from the city of Houston, or the Houston region. And if you notice, it follows very closely to an exact exponential curve all the way until about day 38, 39. And then it looks like it heads off in a different direction. Now, what I want you to see is that there's a change that happened here. What do you think happened around this time that would have made the number of infections that actually happened be different than the number of infections that were predicted to occur by this red graph? So, question number 2. Here they're asking me to talk about the actual difference on day 64. So I'm going to go back to my graph. I see on day 64 we actually have 10,590 cases. But up here, it looks like day 64 would have been almost completely off my graph if whatever event had not happened. So the way that I'm going to do this is I'm going to say, okay, my actual was that number, and I'm going to utilize this line in order to predict what would have happened on day 64. Now, I'm going to go ahead and write down some information first. So my actual number of cases is 10,590. I do not know what my predicted number of cases are. So I'm going to look over here, and I'm going to look at the regression that I run on the data that happened before whatever intervention or action was taken. This regression applies only up to day 39. Why? Because something happened here that changed the course of it. So I want to see what would have happened if we hadn't have done anything. So that's what that equation is. So I'm going to write that equation down. And it's going to look something like this. I wrote in the exact numbers just so I can be as exact as possible. I know that for this, I need to plug in x equals 64. So I can type in this into my calculator to find out what it is. So let's go ahead and do that. And it looks like it should have been approximately 185,000 people. So, if I look at those two numbers, this guy is way smaller than that. So it seems like we had some kind of effect on this. So what I'm going to do is I'm going to find the difference between them. 185,369, I'm going to round up, minus the actual number of cases. And it looks like it's 174,779. So this number is the number of cases that were prevented by us taking action here. Now, my next question is asking me, how long would it have taken if I had just allowed this to progress, we had taken no action to get to the entire Houston region area, to infect every single person in Houston? So, again, let's look at this. I'm going to say, well, X's are days and Y's are people. So that number they gave me has got to be a Y value. So I'm going to go ahead and plug in that Y value in my equation. And I'm going to leave my X as is. And it looks like it's going to give me an X answer. Now, remember that calculators like to be weird about how they solve for X and things. So I plugged in, instead of Y, I plugged in this number, the total population of the Houston region. And I'm looking for this guy. So wherever it touches the X-axis will be my answer. I'm going to zoom in close to the X-axis, and it looks like it's somewhere in between 89 and 90 days. So what does that mean? That means that if we had not taken any action, we would have had everybody in the Houston area infected with this within 89 or 90 days. Now, I want you guys to go ahead and do the same exact process for Texas cases in the entire USA, and then I want you to look at testing in Texas. So this is just how many people have been tested, and I want you to tell me how long it would take for everybody to get tested. Finally, we have a couple of questions that are just about exponentials. So here I gave you a graph of all the different R values for the equations that I created. I want you to take a look at those R values and tell me what that tells you about how close exponentials are to giving us an actual equation of what really happens in real life. Remembering that R values that are on a scale If they're real close to 1 or -1, these guys are strong. But if they're closer to 0, somewhere here in the middle, these are weak. Also remembering, if I have something, for example here, I would say strong positive. Here, weak negative. Here, strong negative. Here, weak positive. Finally, I want you to answer this question. If you notice, every single one of the graphs had some kind of deviation from the curve, the predicted curve. So what I want you to do is to tell me what that predicted curve versus what happened after we took action tells us about social distancing, staying at home, and if that is something that we should continue to do or something that we should always do anytime something like